we started with general transmission line analysis and found out what is the input impedance at a distance from the load. So taking load as the reference, we found out what will be the impedance on the transmission line at a distance, at a certain distance L from the load. And in that we consider the transmission line to be lossy. So we considered the loss components. Then towards the end, we started discussing about lossless transmission line. Politiki ಹುಟ್ಟಿದ್ರು ಕೊಠಡಿ. We started discussing about lossless transmission line. For lossless case, we said that resistance should not be there, conductance should not be there. So L is equal to 0, G is equal to 0. When L is equal to 0, G is equal to 0, then gamma, which is the propagation constant, that will be equal to J beta. Why? Because propagation constant gamma is equal to alpha, which is attenuation constant, plus J beta. Now alpha, the attenuation constant, depends on both R and G. Since both R and G are 0, so the attenuation constant alpha is 0. Therefore, in lossless case, gamma is equal to J beta. There will be no alpha. Now, if we put J beta in place of gamma, then voltage at a distance L from the reference, that is from the loaded end, is equal to V0 plus exponential J beta L, because J beta is gamma. Instead of gamma L, it becomes J beta L into two terms, or 1 plus gamma subscript L, capital gamma subscript L. Capital gamma subscript L is the reflection coefficient on the transmission line. So capital gamma subscript L exponential minus 2 gamma L. Gamma is J beta, therefore minus 2 J beta L. So that is the voltage. Similarly, we found out what is the current earlier. So current will be at the same point at a distance L from the load, or the load being the reference point at a distance L, current will be V0 plus by Z0 exponential J beta L whole into two terms. First term is 1 minus capital gamma subscript L, which is the reflection coefficient, exponential minus 2 J beta L. Now using this, we can find out what is the impedance. Found impedance at a distance L from the load. Why it is minus L? In the expression you can see it is minus L. Reason is from the reference point, that is from the load, we are looking towards the left side. As you know, on the x-axis, if you move towards left side from the origin, then it is negative. If you move towards right side, it is positive. Since reference is the origin and we are moving towards the left side, it is negative. That is why we are writing minus L. So the impedance at the point at a distance L from the reference point or from the load is ZL, that will be equal to V by I, VL by IL. Little data angle side. Now we have found out expression for V, we have found out expression for I. Take the ratio of V to I, that will give you Z0 whole into 1 plus capital gamma subscript L, that is capital gamma subscript L is the reflection coefficient, exponential minus 2j beta L divided by 1 minus the reflection coefficient capital gamma subscript L exponential 2 minus 2j beta L. There now we can use as in the lossy case for gamma L, we can use ZL minus Z0 by ZL plus Z0. If we use ZL minus Z0 by ZL plus Z0 for the reflection coefficient capital gamma subscript L, then the impedance will be Z0 whole into ZL plus JZ0 tan beta L by Z0 plus JZL tan beta L. This is also easier if you find out, uh, if you remember the expression for lossy case. In the lossy case, the expression was same except tan beta L was tan hyperabolic beta L. Sorry, tan hyperabolic gamma L. Now tan hyperabolic gamma L, gamma is equal to j beta. Therefore, tan hyperabolic gamma L is equal to tan j beta L. Tan hyperabolic j beta L. Tan hyperabolic j beta L or tan hyperabolic j theta is equal to j tan theta. So use that. So that gives you tan hyperabolic j beta L is equal to j beta j tan beta L. Will you tell them? Now, if you look at this, then we can find that the impedance is periodic, and it is periodic with a period lambda g by 2. How? Now let us prove that. How it is periodic with period lambda g by 2. Now, and z is a function of tan. So z is a tan function, and we know that the tan function will repeat itself periodically. What is the period in which tan function repeats? The period for repeating tan function is pi. Every pi. When tan theta is 0, then theta is equal to pi, tan value is same. Theta 2 pi, tan value is same. So every pi distance tan function repeats itself. Since tan function repeats itself every every pi distance, therefore beta into L2 minus L1. L2 minus L1 is the distance between 2 points on the transmission line. One point is at a distance L2, so, and other point is at a distance L1. So if it is at L2 and if it is at L1, then if you want to have Z same value, then beta into L2 minus L1 should be pi, because our tan function repeats every pi. Therefore, beta into L2 minus L1 is equal to pi. We know beta is equal to 2 pi by lambda g being the wavelength in the transmission line. So 2 pi by lambda g into L2 minus L1 is equal to pi, or L2 minus L1 is equal to lambda g by 2. So it will be repeated every lambda g by 2, where L2 and L1 are 2 points where the impedance is repeated. So if suppose impedance is 50 ohm at L2, then impedance is also 50 ohm at L1, provided L2 minus L1 is equal to lambda g by 2. Next. Okay, here we summarize everything for the lossless transmission line. The expression for Z, that is impedance at a distance L from the reference point. A reference point is the load impedance where the transmission line is loaded. That is the reference point. Small z is equal to 0. We are finding the impedance at a distance L from the reference point. Therefore, small z is equal to minus L, where we are finding the impedance. then expression for Z will be given by this. Then gamma L is equal to gamma means the reflection coefficient, that is um, ZL minus Z0 by ZL plus Z0. This is summarized. Lambda G is equal to 2 pi by beta. Vp is equal to omega by beta. So this is a summary of the formulas for lossy transmission line. So once we are equipped with this, we can proceed to the next point. Next point is the gamma. Gamma is equal to alpha plus j beta. Now alpha is equal to 0. If you take alpha is equal to 0, then what is beta? Beta is equal to next. Beta is equal to omega root over of LC, that also is equal to omega root over of mu epsilon, because I have already shown you in the last class L is equal to mu, a root over of LC is equal to root over of mu epsilon, that we have already discussed. Therefore beta is equal to omega root LC is equal to omega root mu epsilon, that is equal to K. K is the wave number. Okay. Now, let us consider some special cases. Goodly. Let us consider some special cases. These special cases are important because from a transmission line, using these special cases, we can obtain a, a reactive component. From a simple transmission line can be used as a reactive component using these special cases. Now the first special case is on the short circuited load, which is ZL is equal to 0. So load is short circuited, so ZL is equal to 0. ZL is the impedance of the load. Since the load is short circuited, so there is no impedance, therefore ZL is equal to 0. মাটিটা ভর্তি করে দিল কাটতুছি এতে So since ZL is equal to 0, now what will be gamma L? Gamma L expression we know. Gamma L is equal to ZL minus Z0 by ZL plus Z0. Put ZL is equal to 0, so cancel out ZL from in the numerator and denominator, make them 0. So gamma L will be minus Z0 by Z0, which is equal to minus 1. So in a short circuited load, if the load is short circuited and we are considering lossless case, in that case gamma L is equal to minus 1. So remember this, gamma L is equal to minus 1. For short circuited load, gamma L, which is the reflection coefficient is equal to minus 1. So if gamma L is equal to minus 1, what does it imply? That we'll see later. But I'll just remember that gamma L is equal to minus 1. Gamma L is equal to minus 1. It implies that, let me tell you what it implies. At the load, since it is short circuited, ZL is equal to 0, current is 0, voltage is 0, current is maximum at the load. So voltage will be 0 at that point. Gamma L is equal to minus 1 indicates that the voltage is 0. Gamma L is equal to plus 1 will indicate that voltage is maximum at that point. So gamma L is equal to minus 1 indicates voltage is 0, current is maximum at the short circuit point or at the load point where you are loading the transmission line. At that point it is 1, minus 1, gamma L is equal to minus 1, which means it is short circuited. Now look at the expression for the impedance. So ZL at a distance L on the transmission line from the load. So there you are finding the ZL. Now ZL will be equal to, expression for ZL we have found out. So expression for ZL, we'll put Z subscript L is equal to 0. So Z is equal to Z0 into whole into numerator is ZL plus J Z0 tan beta L divided by Z0 plus J ZL tan beta L. Now if you put ZL is equal to 0, then numerator becomes J Z0 tan beta L, denominator becomes Z0. Z0 in the numerator and denominator will cancel out with each other. So numerator, denominator will be 1. So it will be only numerator which is j tan beta L. Already z0 is outside the bracket. Therefore, z is equal to, when I say z, it means at a distance minus L from the load. So z is equal to j z0 tan beta L. Since z is equal to j z0 tan beta L, we have the term j being the root over of minus 1. So j theta or j a, j b, j x, everything is imaginary. So z is the impedance is imaginary always. Impedance will be imaginary. So if we have a short-circuited load, then the impedance on the transmission line will always be imaginary, either imaginary or 0 or infinity, depending on what is tan beta L. So if tan beta L is not 0 or infinity, it will be imaginary. If it is 0, Z will be 0. Otherwise, if it is infinity, it will be infinity. 0 means it is short circuit. It is equivalent to a short circuit. Infinity means it is equivalent to an open circuit. And otherwise, it will be always an imaginary number. If it is imaginary, z is equal to r plus jx. It is only imaginary means r is equal to 0. So z is in the form jx. Jx means it is reactive in nature. Reactive means it can be capacitive or it can be inductive. So depending on what is the value of tan beta L, if tan beta L is positive, it will be inductive. If tan beta L is negative, it will be capacitive. So as we have seen, ZL is equal to minus JZ0 tan beta L, or you can write Z is equal to JXSC. SC is for short circuit, X subscript XC is short circuit, SC is short form for short circuit. So you can write XC is equal to Z0 tan beta L. If XC is equal to Z0 tan beta L, XC will be positive when tan beta L is positive, XC will be negative when tan beta L is negative. Now, if I draw this, if I plot this as a graph, in the curve of tan beta L, when beta L, so for, let us write beta, what is beta expression for beta L? Beta L is equal to, beta is 2 pi by lambda g, therefore beta L is equal to 2 pi into L by lambda g. Now, if we take L by 2 pi is constant, so let us consider L by lambda g. So in the x-axis we will take L by lambda g. In the y-axis we will take xsc. Now when L by lambda g is equal to 0, then beta L is equal to 0. So tan beta L is equal to 0. So that is the first curve. So that keeps on increasing till L by lambda g is equal to 1 by 4. So when L by lambda g is equal to 1 by 4, then beta L is equal to 2 pi into 1 by 4, which is pi by 2. Beta L is pi by 2 and tan pi by 2 is infinity. So the first part in that range 0 to pi by 2, when beta L is between 0 to pi by 2, it is increasing. It is a function, tan beta L is a function which is increasing from 0. So therefore it is positive. So in that range it will be inductive. Then after beta L is equal to pi, from beta L is equal to pi to beta L, beta L is equal to pi by 2 to beta L is equal to pi. When beta L is equal to pi, 2 pi into L by g, will be equal to pi. From that you can say L by G is equal to 1 by 2. So in that range, tan is negative, tan beta L is negative, because beta L is between pi by 2 to pi, tan beta L is negative. As you know, tan theta is negative when theta is between pi by 2 to pi. So in that range, when L by lambda G is between 1 by 4 to 1 by 2, it will be capacitive. So if the length is such, length of the transmission line section, that L is such that L by lambda G is between 1 by 4 to 1 by 2, it will be capacitive. Then it will be inductive over the next half, then over the next half it will be capacitive. So that way it will continue. So short circuited transmission line can become an open circuit when lambda g by when we have beta L is equal to pi by 2, or lambda g with lambda g by 4 transmission line. When beta L is equal to pi by 2, then L is equal to lambda g by 4. So if it is lambda g by 4, that becomes an open circuit. Infinity means it is open circuit. Zero means it is short circuit. Okay, and now let us consider the open circuited loads. We considered the short circuited load. Let us consider the open circuited load. In the open circuited load, the load is open circuited. So the load is open circuited. Open circuit means the impedance is infinite. So if the impedance is infinite, ZL is infinite. So gamma L will be equal to, that we know expression is ZL minus Z0 by ZL plus Z0. Divide the numerator and denominator by ZL. And because if I put ZL is infinity in the numerator and denominator, then gamma L will be infinity by infinity, indeterminate term. We do not want indeterminate term, so we have to find out what will be the determinant value. So numerator and denominator, divide the numerator and denominator by ZL. If I divide that, then gamma L is equal to 1 minus Z0 by ZL divided by 1 plus Z0 by ZL. In both numerator and denominator, we have Z0 by ZL. Now ZL is infinity, therefore Z0 by ZL is 0. So gamma L is equal to 1 minus 0 by 1 plus 0. 1 by 1 will be equal to 1. So gamma L is equal to 1. Gamma L is equal to 1 signifies that it is terminated in an open circuit. The voltage is maximum at that point, at the termination. Voltage is maximum. Then after every lambda g by 2 distance, voltage will be maximum. Every lambda g by 4 distance, voltage will be minimum, current will be maximum. This will also prove in the next slide, and that we'll discuss later. Now gamma L is equal to plus 1. Now that is what we know. That also indicate, like gamma L is equal to minus 1 and gamma L is equal to plus 1. What is the difference? Difference is whatever we are incidenting, the voltage, that is the incident voltage, gets completely reflected. Gamma L is equal to 1 means complete reflection. So plus minus 1 means it is complete reflection. Plus 1 is in phase. What is the phase of the incident wave is the phase of the reflected wave. Gamma L is equal to minus 1 indicates that what is the phase of the incident wave is 180-degree out of phase with the reflected wave. So that is the difference between plus 1 and minus 1. Okay, now let us come to the impedance at a distance L. Let us come to the impedance at a distance L from the load. Load is at Z is equal to 0. Now we are considering at Z is equal to minus L, small z. Small z is equal to minus L on the transmission line, any point on the transmission line which is at a distance L from the load, which is the reference point for which small z is equal to 0. So now any point for which small z is equal to minus L, there the impedance expression is ZL plus JZ0 10 butyl by Z0 plus JZL 10 butyl whole into Z0. Now, what I'll do is divide the numerator and denominator by ZL. If you divide the numerator and denominator by ZL, then this expression becomes Z0 whole into 1 plus J Z0 by ZL 10 butyl divided by Z0 by ZL plus J 10 butyl. Now, Z0 by ZL is equal to 0 because ZL is infinity. So, Z0 by ZL is equal to 0. Put that 0, then Z at a distance L from the reference point is equal to Z0 whole into 1 by J tan beta L. So that is same as Z is equal to minus J Z0 cot beta L. So Z is equal to minus J Z0 cot beta L. Since we have a J term, therefore it is always imaginary. The impedance will be always imaginary on the transmission line unless cot beta L is equal to 0 or cot beta L is equal to infinity. Under these two conditions, it will not be imaginary, it will be either 0, which is short circuit, or it will be infinity, which is open circuit. So it can be the transmission line of a section L can be short circuit or open circuited transmission line that we'll see now. Now we are writing this Z is equal to minus J Z0 cot beta L, that you can write again as J is equal to J X subscript OC. OC is for open circuit. We are considering open circuited load, therefore XOC. So XOC, that is the reactance part, is XOC. So the transmission line section can be reactive or short or open. So if it is reactive, then XOC is equal to minus Z0 cot beta L. Now again we know beta L is equal to 2 pi by lambda g, that we know as in the previous case. Now here lambda g is equal to lambda L. Lambda g is the guided wavelength. Lambda L, here guide is the transmission line. Therefore, at a distance L, we are finding it lambda L on the line. So lossless case, lambda g is equal to lambda L for the lossless case. Now let us again draw the curve plot for this one. XOC is equal to minus Z0 cot beta L. If we plot it, then on the x-axis we will take L by lambda g as in the previous case. On the y-axis we will take XOC. Now, when beta L is equal to 0, in that condition, when beta L is equal to 0, then cot beta L is positive, minus JZ0 cot beta L will be so negative. When it is 0, it is infinity. As you know, cot beta L, cot 0 is infinite. So for beta L is equal to 0 or L by lambda g is equal to 0, XOC is negative infinity, which means it is negative infinity means it will be open circuited and it will be capacitive from that point up to L by 1 by 4. When L by lambda g is equal to 1 by 4, then it will become short circuited. Why it will become short circuited? When L by g is equal to lambda by 4, sorry 1 by 4, beta L is equal to 2 pi into 1 by 4, which is pi by 2. So beta L is pi by 2, cot beta L is cot pi by 2, cot pi by 2 is 0. Therefore, if it is XOC is equal to 0, so it is short circuited. So open circuit, although it is open circuited transmission line at a distance L, such that L by lambda g is equal to 1 by 4, this line behaves like a short circuit. So open circuit can become a short circuit with a lambda g by 4 transmission line. Okay, and so after that, from L by G is equal to 1 by 4 to L by G is equal to 1 by 2, it will be inductive. Then L by G is equal to lambda 1 by 2 to L by G is equal to 3 by 4. It will be capacitive. So this way it will keep on continuing, uh, repeat itself every lambda G by 4. Okay. So then we will come to the final stage of the special case, which is the matched load. Matched load means the characteristics impedance of the transmission line, which is Z0, matches the load, which is equal to the load. So load value ZL is equal to the characteristics impedance. So terminate the transmission line with a load, so whose value is equal to the characteristics impedance of the transmission line. That is ZL is equal to Z0. Under that condition, gamma L is equal to ZL minus Z0 by ZL plus Z0. Now, since ZL is equal to Z0, numerator becomes 0. So, if numerator becomes 0 and denominator is non-zero, then gamma L is equal to 0. If gamma L is equal to 0, reflection coefficient is equal to 0, which means there is no reflection from the load. By definition, you know what is reflection coefficient? It is the reflected voltage by the incident voltage. Now, since the reflected voltage by incident voltage is equal to 0, which means reflected voltage is equal to 0. Since reflected voltage is equal to 0, there is no reflection. That indicates that there is no reflection from the load. So, if you have a matched load,
Sir,
yes,
sir, କିଛି PPT show କରୁନି।
PPT show କରୁନି. Okay, okay,
ନାଇଁ
let me
sir,
try.
କିଛି show କରୁନି।
Okay, ମୁଁ ଦେଖୁଛି। ଦେଖିଲୁ PPT show କରୁନି କ'ଣ ପାଇଁ? ସେୟାର ହେଇନି କି? ହଁ। କୋଉ ଯାଏଁ PPT show କରୁଥିଲା? ଏବେ ଦେଖାଯାଉଛି?
ହଁ sir,
କୋଉ ଯାଏଁ ଦେଖାଯାଉଥିଲା ମତେ କହିଲ, ମନେ ଅଛି?
sir ଏବେ 3 minutes ହେଲା ବନ୍ଦ ହେଇଯାଇଥିଲା।
3 ମିନିଟ୍ସ ହେଲା ବନ୍ଦ ହେଇଯାଇଥିଲା। ଆଚ୍ଛା।
ହଁ
ତ
sir,
ମ୍ୟାଚ୍ ଲୋଡ୍ ଦେଖିନ, ତା ପୂର୍ବରୁ ସର୍ଟ ସର୍କିଟ ଓପନ ସର୍କିଟ ଦେଖିଲ?
ହଁ sir,
ଓପନ ସର୍କିଟ ବୁଝିଛ?
sir ଟିକେ doubt ରହୁଛି।
ହଁ କୁହ, କ'ଣ ଡାଉଟ୍ ଅଛି କୁହ? ଓପନ ସର୍କିଟ ଦେଖିଥିଲ ତ?
ହଁ sir,
ତା ପ୍ରେଜେଣ୍ଟେସନ କରିଦେ। ନାଇଁ ଓପନ ସର୍କିଟ ଯା। ହଉ। When you have doubt, please ask me at that point immediately. Otherwise, when I'll take a break, you can ask me that. Okay. So let us consider the matched load case. In the matched load case, what happens is the characteristics impedance of the transmission line and the terminating impedance of the transmission line are same. So the load impedance which terminates the transmission line is equal to Z0, where Z0 is the characteristics impedance of the transmission line. If Z0 is equal to ZL, in that case Z0 is equal to ZL or ZL is equal to Z0. Now when ZL is equal to Z0, gamma L, which is the reflection coefficient, that will be equal to ZL minus Z0 by ZL plus Z0. ZL minus Z0, since ZL is equal to Z0, so numerator will become 0. So gamma L will be equal to 0. Gamma L is equal to 0 indicates that there will be no reflection from the load. Everything, all the power that comes to the load will be absorbed by the load. Load will take all the power. It will not reflect any power or any energy from the load. Now, why that happens when gamma L is equal to 0? Why there will be no reflection from the load? You know, by definition, gamma L is the ratio of reflected voltage to the incident voltage. So, reflected voltage by incident voltage is equal to 0. Incident voltage cannot be infinite. So, since we cannot have practically, you cannot have infinite voltage, incident voltage cannot be infinite. So, for it to be become 0, reflected voltage has to be 0. So reflected voltage is equal to 0 indicates that there is no reflection from the load. So there will be no reflection from the load. Now what will be the impedance Z? Z will be equal to Z0 into 1 plus gamma L exponential minus 2 gamma L divided by 1 minus gamma L exponential minus 2 gamma L. Now gamma L is equal to 0 we have found out. Therefore Z will be equal to Z0. So for any Z anywhere on the transmission line, this is the special case, only case in which everywhere on the transmission line you will find the same impedance. If the transmission line terminates in a matched load, then on each point on the transmission line you will get the same impedance which is equal to Z0. So this is the special case of a transmission line which terminates in a matched load. Now let us consider a quarter wave transformer. What is called a quarter wave transformer? That we'll discuss now. Now in this case what happens is we take a transmission line whose length, the section of the transmission line, length, a section of transmission line we consider, its length is lambda g by 4. So L is equal to lambda g by 4, a quarter of the wavelength, lambda g being the guided wavelength, length of the transmission line is a quarter of the guided wavelength. That is what is important. Important is the length of the transmission line is a quarter of the guided wavelength, and at one end the transmission line is terminated in a load. The load impedance is ZL. The characteristics impedance of the transmission line is over this length, over this quarter wavelength is Z0T, and that the other end of the transmission line is connected to another transmission line whose characteristics impedance is Z0. So we have a transmission line whose characteristics impedance is Z0. That transmission line, the end of the transmission line is connected to a section of transmission line whose characteristics impedance is Z0T and whose length, the section of the transmission line length is lambda g by 4, or the length is a quarter wavelength of the guided wave length, quarter of guided wavelength, and that is terminated in a load ZL. So what will be Zin? Zin will be equal to the Zin is the input impedance, and that you see from the first transmission line whose characteristics impedance is Z0. From that end you see the second transmission line at the junction of the two transmission lines with characteristics impedance Z0 and Z0T. Exactly at that junction the impedance is called the input impedance, because you are inputting power from the transmission line whose characteristics impedance is Z0 to the transmission line whose characteristics impedance is Z0T. You are giving power input to the second transmission line. Therefore, it is called input impedance. So, Zin will be equal to Z0T, the characteristics impedance of the second transmission line, whole into ZL plus JZ0T tan beta L divided by Z0T plus JZL tan beta L. This is the expression that we know. Now beta L, we know beta L is equal to lambda g by 4. So beta L is equal to beta into lambda g by 4. Beta is 2 pi by lambda g. So 2 pi by lambda g into lambda g by 4. Lambda g cancels out. 2 in the numerator, 4 in the denominator. So denominator becomes 2. So beta L is equal to pi by 2. So for tan beta L, if we put tan pi by 2, then Z in now will become Z0T whole into J Z0T by J ZL. Now J will cancel out. So Z in will be Z0T into Z0T by ZL, or Z in is equal to Z0T square by ZL. So that is what we get. Z in is equal to Z0T square by ZL, or Z0T square is equal to Z in into ZL. This is an expression that we found. From that you can say Z0T is equal to square root of Z0 into ZL. So what happens here is, if the characteristics impedance, we can transform the the load impedance ZL to another impedance. That is what we are doing. So ZL is transformed to Z0 using a quarter wave length. Now, what is the matching condition? Under matching, if the transmission line is properly matched, then gamma in is equal to 0. If gamma in is equal to 0, that implies that Z in is equal to Z0. That we have already seen from the matched load condition in the previous slide. We saw the matched load condition. In the matched load condition, we saw gamma in is equal to 0 if it is matched. So gamma in is equal to 0. That indicates that Z in is equal to 0. Now we have seen Z in is equal to Z0 square, Z0 T square by ZL. So for Z in we can put Z0. If we put Z0, then Z0 is equal to Z0 T square by ZL. So this requires that ZL has to be real, otherwise this square will not hold. Z0 into ZL will not be Z0T square. So for that will not hold. Therefore ZL has to be real. Z0 is real, ZL has to be real. Z0T square will be Z0T whole square will be real. So from that we get Z0T is equal to square root of Z0 into ZL. So now let us see one example of this quarter wave transformer. Then we'll take a break. You can ask me questions, whatever questions you have. Now under this condition, we are trying to match a 100 ohm transmission line to a 50 ohm transmission line at a given frequency. Frequency can be anything. So we are trying to match a 100 ohm load to a 50 ohm transmission line. So the first transmission line, its Z0 is equal to 50 ohm, ZL is equal to 100 ohm. We want to match this ZL to 50 ohm. So in between these two, the load and the transmission line, 50 ohm transmission line, we are going to insert another transmission line whose length is lambda g by 4 and whose characteristics impedance is Z0T. So on this section of transmission line with lambda g by 4 quarter wave length transmission line will match the load ZL to the transmission line whose characteristics impedance is 50 ohm. That is the purpose. For that Z0T we have to find out what will be Z0T. Z0T is equal to square root of Z0 into ZL. That we have already seen. Therefore Z0T is equal to square root of ZL is 100 and Z0 is 50. So square root of 100 into 50. So that is 70.7. So Z0T has to be 70.7. And now about the length, what will be the length? Length is lambda g by 4, and it will depend on the frequency. As you know, wavelength depends on frequency. So lambda g, it is 2 pi by beta, that is equal to 2 pi by k, that is called beta is equal to k, and k is equal to k0 into root over of epsilon r. Epsilon r is the permittivity of the dielectric medium which is filling the transmission line, connecting transmission line with characteristics impedance Z0T. So this will be lambda g is equal to 2 pi by k0 root over of epsilon r. If it is free space, there is no dielectric filling the transmission line, then lambda g is equal to lambda 0. Anyway, now here it will be 2 pi by k0 root over of epsilon r. 2 pi by k0 is lambda 0. So it is lambda 0 by root over of epsilon r. What is lambda 0? Lambda 0 is free space wavelength, that is equal to c by f. C is speed of light, f is the frequency. So if you know what is the frequency at which you are matching it, then you can find out what is lambda 0. Once you know what is lambda 0, you can find out what is lambda g, that is lambda 0 by root over of epsilon r. Once you know what is lambda g, you can find out what will be lambda g by 4. So what will be the length of the transmission line section. So that is how you do. That is how you will do the matching of transmission line. So with this, we'll take a break here, a break for 10 minutes. You can relax. You can ponder upon what we discussed. I have already supplied you the notes. So if you have any doubts, you can ask me the doubts from in this break.